All right, y'all. So in class, the last thing that we did is we looked at how horizontal and vertical motion is independent of each other, right? We looked at the ball that was dropping, we looked at the ball that was being shot, and we found that the vertical motion, they were both dropping at exactly the same rate. Now, in today's video, I just want to kind of reiterate that. And so we're going to look at some graphs. We're going to look at some situations where we have an object that's being shot horizontally off of a cliff. We're going to look at it just kind of normally, assuming that there's no air resistance. And then we'll look at a situation where there is air resistance causing it to slow down. And then we'll look at a situation where it's maybe got some extra thrust there, like maybe some type of rocket, and it's going a little bit faster. So we'll look at those three situations. What I want you to be thinking about as we look at these is we're showing the horizontal components and we're showing the vertical components independent of each other, but then we're putting those together to get the total of what the rocket or what the ball is doing. All right, I want you to think about Newton's laws. When is Newton's first law applying horizontally and or vertically? And when is Newton's second law applying horizontally and or vertically? We won't worry about Newton's third law here. The interaction between the two objects won't be important. All right, the last thing I want you to think about is how are each of these graphs the same or how are they different? And so as we look at those, hopefully you'll recognize some of the things that are always going to be the same and some things that are going to change depending on the situation, depending on what's happening. But the big idea, of course, here is that we're going to keep our vertical and horizontal components independent of each other, that they can act independently, different things can happen. We're going to try to do that as much as possible in this class, and this is just an introduction to that. So come on, let's go give it a try. So we're going to work through this worksheet together about components in motion. And we're going to look at a couple of different situations about an object that starts moving horizontally, but as it moves horizontally, gravity is pulling it down, causing it to accelerate. What we want to do is we want to look at what's happening as that happens. So we are starting with this horizontal velocity right here. Now, as something gets thrown, we're going to assume that it's being released right here at this point. So it's being thrown. So the horizontal velocity, there are no horizontal forces here. And so the horizontal velocity is going to be the same as what it was when it was thrown. However, the vertical, it's going to be pulled down just a little bit. And so what we're going to do here is we're going to add on a vertical vector right here. Now, when you add those two together, the horizontal, which is blue, and the vertical, which is red, the result is a vector that looks like this. Starts here and goes to there. I'm going to add on the arrow there just so that it's clear. So that's what it's doing now. Now, after a certain amount of time, the horizontal is going to stay the same. So I'm going to draw my horizontal. So this is after, you could just say 1 second or whatever time you want to say. So we're going to go ahead and add on. So now the horizontal is not changing. There are no horizontal forces here. So the horizontal is not being affected. So we go 1, 2, 3, 4, 5. So the same length as it was before. The vertical, however, is changing because gravity continues to pull down. All right. So now instead of the vertical being 1 square, the vertical is now going to be 2 squares long, just like that. Now at this point, we can go ahead, we add those two together. It's got that horizontal motion and the vertical motion, which is increasing, getting a little bit faster, traveling a little bit further in the same amount of time. And my result is now something that looks something like this. All right, now we're going to repeat that a couple more times. Recognize that in each step, the horizontal is not going to change. The horizontal velocity stays the same, so it travels the same horizontal distance in the same time that it did before. The vertical went from 1 to 2. It's going to continue accelerating in that vertical direction, so it's going to have now 3. It's going to go down to 3 there, just like that. And when we draw in the result of those two, we now show that the object has started pointing down a little bit more. Now this should look somewhat familiar. This is what happens when you throw something, that it kind of starts curving down just like that. Okay, when you throw something, it doesn't go in a straight line and then just drop all of a sudden. It kind of curves down just like this. Now, let's go ahead and add on a couple more. I'm going to speed up the video. You get the idea now. There we go. So we added on a couple more there. You can see how each time the horizontal velocity is staying the same as time passes. The vertical velocity gets longer and longer. So the vertical velocity is increasing, just like we expect something that gravity is pulling down on. So there's a vertical acceleration, but the horizontal is constant. Now, that results in the curve that we expect of something that gets thrown, that it starts curving down more and more and more, and it just kind of follows this path here. Now, we did it in kind of bits and chunks and pieces, but you can imagine that this is always happening. It would give you a nice, smooth curve there. All right, now it does get steeper and steeper and steeper, right? That makes sense because the run, remember slope is rise over run, the run is always the same, but the rise, which is negative here, gets longer and longer and longer. So that should make that velocity steeper and steeper and steeper. All right. And hopefully you can answer the other questions on the worksheet at this point, but that's the big idea, is that it is doing this. Now, one thing that I do want to note is that we started right here, and after 1, 2, 3, 4, 5, 6 segments, it has traveled a total of 30 squares, 30 units. Okay, whatever that is, from one end all the way to the other end. All right, that'll be significant when we look at some more of these graphs here in just a minute. All right, so let's move on to question number 2. So you can read through question number 2. You'll note that question number 2 is going to be very similar this time, except we're not going to ignore air resistance this time. In the first one, we just assumed that the horizontal kept staying the same every single time and that the horizontal never changed because there was no air resistance. This time, we're going to assume that as the ball moves in this direction, that the air resistance or some friction is opposing it and working against it. We're going to do that by just making the horizontal vector 2 millimeters shorter each time. So slightly shorter than it was the previous time. All right, so same thing's going to happen here. So if we follow the steps here in D, we're going to draw the horizontal vector. So we're going to start off with it being 5 squares long, which is 2.5 centimeters. And then we're going to add the vertical vector, which here at the beginning is just that 1 as gravity starts to pull down on it. We'll draw the resultant vector right there, and we now have point B, which is going to be right here. So that right there is point B. All right, now we're going to repeat that. This time, however, we're not going to keep the horizontal the same because we're going to say the horizontal is going to be affected by air resistance. So I'm going to take off about 2 millimeters, so it's going to go to about right there. Okay, so it's going to go to that point right there, just like that. Now, the vertical gravity is still pulling down, so we're going to assume that gravity still pulls down at about the same before. Remember, it went down 2 squares now. And so now we add in our resultant vector here. There we go, just like that. And we can add in, we'll just continue that. That's now point C there. And we can keep doing that. We're going to repeat it. It says 5 cycles. I did the last one for 6 cycles, so let's go ahead and do that. We're going to do 6 cycles here. So this one, I want to make sure that it is, you'll notice that my centimeters here match up with the squares, which is just what I was hoping for. So the last one, the first one was 2.5. This one was 2.3. So this one I now want to go 2.1 centimeters, so it's going to go to right there. This isn't perfect, but it'll be enough that you'll be able to get the idea. The one going down is now going to be a little bit longer, so it's now going to be 3 squares right there. And so you'll notice that horizontal is getting a little bit shorter. It still looks really, really similar to what we had before. That's now point D. All right, so I now have 1, 2, 3 iterations. I think hopefully you've got kind of the idea. The last one was 2.1, so this one we're going to go 1.9 just to right there. And I'm going to go ahead and speed this up now to try to wrap this up. All right, so there we go. Have a look at that. How does that look compared to the original one? Well, let's see. You can see now that this time, that horizontal, though it was originally that, it got a little bit shorter, so that horizontal, because of the air resistance, the horizontal is getting shorter and shorter and shorter. What result is that having on the object as it flies through the air? Well, hopefully you're seeing that it's not traveling as far, right? If I were to measure this one, the first one was 30 units, right? Went all the way up to 15 centimeters here. Now, if I measure this one, it looks like it only goes up to a little past 12. Now, I didn't do this perfectly. I'm using a fat old marker here, but so as long as it's something close to that, you're recognizing that we only got up to 12, which is about 24 units this time, which is definitely not as far, which makes sense because we've added in air resistance. What else is different? Well, notice that the rate of falling is the same, right? Those vertical things are exactly the same. It dropped exactly the same distance down. If I put them side by side like that, they start at the same height. They ended down at the same point as well. Okay, this graph was a little bit shorter, so it doesn't quite fit. But if you put it right next to each other, you can tell that the vertical did not change. It still had to drop exactly the same distance. All right. It does get a little bit steeper down here. That's actually what you see when you throw things, is that they do get steeper, even more steep than it was in this one, because there is some air resistance causing a little bit of change there. All right. So we're starting to get an idea of this horizontal and vertical are independent of each other. They can do things differently. The vertical is accelerating downwards, getting longer and longer and longer. The horizontal is accelerating as well. It has an acceleration in the opposite direction. The force is opposing that motion, right? We've been talking about Newton's laws. In this first one, thinking about Newton's laws, horizontally, there are no forces. And remember, Newton's first law said that if the forces are balanced, then the object should maintain its state of motion. So that we see that there are no horizontal forces, so the horizontal motion continues exactly the way that it was before. The vertical motion, there is a force. So you've got a vertical force there, which means that the vertical motion should follow Newton's second law, which is that the acceleration is proportional to the force, which means that it should be getting longer and longer and longer, just like it does. This one is slightly different, just in that we're saying that there is a horizontal force. The horizontal force is the air resistance pushing against our object as it flies through the air. That horizontal force is going to cause a horizontal acceleration, causing it to get shorter and shorter and shorter. That does not affect the vertical motion of the ball. Now, in a real situation, you should have both horizontal and vertical acceleration, but we're trying to simplify things a little bit here. All right, let's look at another situation. Here we've got a rocket being shot horizontally off the edge of a cliff. So this time the rocket is going to be firing its boosters. It's still going to start with the same speed that the original one did, because we're still going to throw it off the edge. But once it's off, it's going to be firing its boosters, and so it's going to actually be getting faster and faster as time goes on. Now, again, remember that horizontal and vertical are independent of each other, and so we're going to try to represent that here. So, just the same as before, we're going to go ahead and draw our 2.5 centimeters there, just like that. And it's going to fall just a little bit. Okay, acceleration is down, and we add in the result there, which is that it's now moving kind of in that direction. That's going to be our, I guess if this is A, this would be point B. All right, then the same thing's going to happen. But this time, because we got a rocket booster, this is going to go from 5 squares to have an extra centimeter, half a centimeter on there. So we're going to go to 6 squares now. 1, 2, 3, 4, 5, 6. So now it's going to be accelerating in that direction. But the horizontal and vertical do not affect each other. So the vertical now is still just going to be accelerating downwards because of gravity pulling it down. The rocket firing horizontally does not affect the fact that gravity's pulling down on it. A lot of people, when you get to something like a gun, people are like, oh yeah, the gun, the bullet goes in a straight line. No, bullet doesn't go in a straight line any more than a ball goes in a straight line. It's just it travels further in the same amount of time. Bullet will take the same amount of time to hit the ground as a ball does. It just travels a lot further in that amount of time. So we've got point C there. Oh, sorry, I forgot to, I should focus on drawing, not on talking, but that's okay. Here we go. Moving on. So the next one, a little bit faster. That rocket is still firing. So now it's going to be 3.5 centimeters, just like that right there. And we'll go ahead and add in acceleration, which acceleration again is going to go 1, 2, 3. So it's a little bit faster now. The acceleration is constant, right? That means the velocity is changing by the same amount every single time. What we're drawing here are the velocity vectors, and we're trying to use those velocity vectors to give us an idea of what is happening to the position over time. All right. So we'll go ahead and add in the next one. So the next one is now going to be, so I went from 2.5 to 3 to 3.5. Now I'm up to 4. All right. So I only went 1, 2, 3, 4, 5 iterations this time, because I'm obviously running out of space both below and on the side, which is fine. You'll get the idea. Notice that it's not perfectly straight. It may look straight, but it is still curving a little bit, right? Even though it's got acceleration in both directions, even though it has the same acceleration in both directions, it is still curving downwards, okay? Because the vertical is changing relatively by more than the horizontal is, right? The vertical is doubled from there to there, whereas it only added about 25% there. So it is getting longer and longer, but it is still curving down a little bit, okay? It is still eventually going to hit the ground. What I want you to notice is after the first 5, let me get back to our original one here. So if I go back to the original, notice that if I start up at A, right there, after 1, 2, 3, 4, 5, that would be right here. Notice it's still at exactly the same height because we haven't changed the vertical acceleration. The vertical acceleration has been the same for question 1, question 2, and question 3, and we see that that vertical acceleration is constant. And remember that the vertical motion is not affected by the horizontal motion. Okay, the overall horizontal distance is changing, right? This one's definitely traveling a lot further than that one would in the same amount of time, but the vertical is not changing, therefore the vertical motion will stay the same. And it will take the same amount of time for the object to finally get down to the ground, right? It would only take me one more iteration, that 6th iteration, before it would get down to exactly the same place that this other one was. And so recognizing a lot of different things, it doesn't matter what's happening to X, it's never going to affect the Y. It doesn't matter what's happening to Y, that is not going to affect the X. Those perpendicular components are independent of each other, and they will do whatever they're supposed to do by themselves. All right, that's it for this one, and I hope that was helpful. We'll see you later.